So now we're going to wrap this section up by discussing a geometric interpretation of the cross product. And what I mean by that is that I'm going to give you, at least in theory, a way to compute the cross product of two vectors without referring to their coordinates, right? And think about what you'd need to be able to do that. You need to be able to come up with the length of the cross product and the direction of the cross product, right? And really all you would have access to in order to come up with that is the length and direction of both of the factors u and v. So that's the idea behind what we're going to do. And we're going to start with direction. So if you have two vectors, u and v, that are three-dimensional vectors, right? Because of course we can only even talk about the cross product for three-dimensional vectors. I just want to take a moment to remind you of that. There is no notion of the cross product of any vectors except in R3. Okay, well, how can you get the direction of u cross v, assuming that you have only the direction of u and v? That's the question. And we're going to use the following rule, and it's called the right-hand rule. Okay, and the way the right-hand rule works is the following. You're going to take the vectors u and v, the ones that you're presumably considering the cross product of over here, and you're going to draw them so that their initial points coincide. And you're going to do it so that they look like this. And this is always possible, although you might have to move your perspective in order to do it, right? You might have to turn your head sideways or even upside down to make it happen, right? But you can always orient yourself and change your perspective so that when you look at the vectors u and v drawn with the initial points coinciding, they look like this. But that's the first step to determining the direction of u cross v. Now, remember that one of the first things we said about cross products is that they're always going to be orthogonal to the two factors that you started with, right? That's properties 1 and 2 on this page, on the first page. So, right, because u is orthogonal to u cross, well, I guess it was over here that we wrote it, right? U cross v is orthogonal to u, and it's also orthogonal to v. So if you look at this picture, and remember this is a picture in 3 dimensions, there's really only 2 places that u cross v could go in terms of direction, right? It could point straight up, and then it would be orthogonal to both of those vectors, or it could go straight down, and then it would still be orthogonal to both of those vectors. But it's certainly not going to say point that way, or that way, or this way, right? That wouldn't make sense. Whatever direction that u cross v points, it has to be orthogonal to both u and v. So there's only 2 directions that are possible, up or down. Those are the only 2 candidates. But you can figure out which one using the right-hand rule as follows. So here are the 3 steps. The first step is to point your index finger in the direction of the vector u. So this is a bit of a goofy drawing, but it works. It does the job. So draw an index finger pointing in the direction of u. That's how you should interpret that, right? It's pointing, this is the tip of your finger, and it's pointing right along the direction of u. And now the second part of this is that your fingers are going to curl in the direction of v, right? So your fingers could curl that way, or they could curl this way. That's the 2 options. So if the finger is pointing towards u and v is over here, and the fingers are curling towards v, they're going to curl towards us. So the way I would draw that is just like this. It's a bit kind of cartoony, but that's how you can think of the fingers. And now you can finish the hand like that. Like I said, it's a silly drawing, but that works for a hand. And the third step here is that your thumb is going to point in the direction of u cross v. And based on the way we've drawn it, you can just imagine there's only one place that your thumb can point. Your thumb's not going to point downward at this stage if that much of the hand is already drawn. The only way your thumb can point is upward. And maybe that thumb is a bit big for how big a thumb would be relative to everything else, but you get the idea, right? So that tells you that you can now draw u cross v, or at least draw the direction, right? The length might not be correct, but at least the direction is going to be correct. We know that the direction is going to point up like this. So basically your fingers will have been wrapping around the vector u cross v. That's the idea behind the right-hand rule. So this, I'll just say this points in the direction of u cross v. Right, I didn't say it is u cross v, because again, we don't know necessarily the length of u cross v at this stage, but we do know that this vector that's pointing upward, that points in the direction of u cross v. So that takes care of half of it, right? Because remember, geometric vectors are characterized entirely in terms of their length and direction, and we now have the direction, at least in terms, if we assume that the directions of u and v are known, then from that we can get the direction of u cross v. But the other part of the other issue now would be, well, what about the magnitude of u cross v, or the norm of u cross v? So can you get the norm of u cross v in terms of just if all you had access to were the norms of u and v separately? And the answer is yes, and this is how you can do it. Then we're going to start by looking at property 3 again that we had on the previous page. So I mentioned that we wouldn't use this very much, and really this is the only time we're going to use this property. So this tells you that the norm of u cross v, at least if you square it, is given by this expression over here. And you can see you've got the norm of u squared and the norm of v squared. So that almost takes care of it, except you still have the dot product of u and v. And the dot product of u and v depends on more than simply the lengths of u and v respectively. So this property isn't quite going to be enough, but it turns out if you do some manipulations, it turns out it is enough. So that's what we're going to start with. I'm going to start with this property. So what it says is the square of the magnitude of u cross v is equal to, we get the square of the norm of u times the square of the norm of v, and then remember you subtract the square of the dot product of u and v. Okay, and recall that because we're dealing with vectors u and v that are in R3, we have access to the geometric definition of the dot product. So I'll just remind you, it's given by this u dot v is equal to the length of u times the length of v times cosine of theta. Remember, when theta is the angle that the vectors form if you draw them so that their initial vectors coincide. I'm not going to draw that picture yet again. I've drawn it plenty of times. But you could actually, we could just think of it up here, right? If this is the vector u and this is the vector v, then that angle between them, that is really what this value theta is. Okay, so let's apply that to this dot product here and see what we get. Well, we're going to get the norm of u squared times the norm of v squared, that part won't change, minus, so then for dot product of u and v, just plug in all of this. So we're going to get the norm of u times the norm of v times cos of theta, all squared. But these are just three real numbers here. Norm of u, norm of v, and cos theta. Those are all real numbers. And if you square their product, it's just going to turn it, this squared can just be applied to each of the factors separately. And if we take advantage of that, we're going to get the norm of u squared times the norm of v squared minus, and then what will happen here, we'll get the norm of u squared again times the norm of v squared times cos of theta all squared, which typically you would just write that as cos squared of theta. So that's what you get. And now you've got two terms that have a common factor of the norm of u. In fact, they got a common factor of the norm of u squared. So we can pull out a norm of u squared. We can even pull out a norm of v squared as well. So why don't we pull them both out in this one step? So we're going to get the norm of u squared times the norm of v squared. And it's going to be multiplied by 1 minus cos squared of theta. And another thing that we're going to take advantage of is that the Pythagorean identity for trig, if you don't remember this, no problem, I'm just going to remind you of it now. Sine squared of theta plus cos squared of theta is always equal to 1. So let me just remind you, this is called the Pythagorean identity. So we can use that here. So what would happen if I subtracted cos squared to the other side of the equation? I'd have sine squared of theta is equal to 1 minus cos squared of theta. Right, so really what that means is that this here is actually equal to sine squared of theta, right, using the Pythagorean identity. right? Just take this cos squared of theta and move it over to the other side. And you're going to get sine squared of theta is equal to 1 minus cos squared of theta. So that's what we're applying down here. So what we actually get here is the norm of u squared times the norm of v squared times sine squared of theta. And we're almost done now, actually, because, well, if we take the square root of both sides, just use the fact that this expression is now equal to this expression. Well, we can take the square root of both sides, and we get the length. I'll use the therefore symbol. Therefore, the length of u cross v is really just equal to the square root of this expression. So I'll just get the norm of u times the norm of v times sine of theta. So we do actually still have to have that theta as part of our formula. We can't escape that. So the orientation of the vectors u and v, in the sense of the angle that they form when you draw them in this fashion, that's going to play a role in determining the magnitude of u cross v. So you will use this for one of the exercises in this chapter, and the question actually reminds you of it, so there will be no surprise when you get there. When you get to that exercise, you'll know it. It'll tell you explicitly that you're going to use this identity, but really that's the only time in the course when we use it. So it's not going to be something that we use a whole lot, but it is nice to have for theoretical purposes. So just to summarize what we've done on this page, we've given now a geometric interpretation of the cross product, what that means is you can get the direction of the vector u cross v from the right-hand rule, and you can get the magnitude of the vector u cross v with only the following information given to you in advance: the length of u, the length of v, and the orientation of u and v. In other words, the angle that they form when you draw them, so that the initial points coincide, like this picture here.